How are you, Elliot?
Good. How are you?
Hanging in there.
Yeah.
You gonna do anything for Christmas?
Grade papers.
Glad to hear it. So how did it go? So you taught on Zoom, I assume.
Yep.
How'd it go?
It's not too bad. I mean, I think in terms of lecturing, it's not all that different.
Uh-huh.
But dealing with exams and people in other parts of the world, that gets complicated.
Yeah. How do you make sure they don't cheat, work with each other?
I don't think there is any way of doing that. I mean, I give the exam on Zoom. They're all on camera, but there are obviously many ways that they can,
right.
They could cheat.
But anyway,
I've been giving take-home exams instead.
And they're supposed to be on Zoom while they're taking them.
Yeah, I mean, yes, everybody's supposed to be sitting there.
Yeah.
Dave, what did you say about take-home exams?
I switched to take-home exams, and first of all, I have a pretty good memory for weird details. I can spot cheating. I mean, it's like if people are dumb enough to need to cheat, they cannot hide 100 little clues that they copied it from someone else. But what's radicalized me is different people are excelling. I mean, most of my perfect scores come from people who describe some kind of ADHD or some weird neurotypical. And I say, wait till you meet mathematicians. But I mean, it's like, it's not a time trial. What you do isn't in 75 minutes. It's what you do in a lifetime.
Yeah.
And it's like they're like tech firms are deciding that the speed interviews are not really finding the right people either. Programming competitions don't make the best programmers.
In a course like calculus, which is what I taught, it's just so easy to go onto one of these websites like Symbol Lab or Wolfram Alpha and look up the answers to a problem if I want to get a test.
I tried making the problems a little more interesting for that.
Yeah, I've thought about that.
It didn't really, it's easy to go overboard, trust me. I lose as many people in the middle section in linear algebra on inner products as I ever did. Even I made the problems a little more challenging. Of course, my last problem for the final I'm putting up tonight, starts with a family of matrices, and you're going to solve the Jordan form to get the closed form formula, and there happens to be repeated root, but I'm going to see who does that. Maybe 3 out of 60, I mean.
All right. So I'm going to finish today. I may have to be brief at various points, but I'll try to give you an overview. So we've been studying the space that we've called FIQ. So these are ordered Morse functions with critical points of index I and I plus 1 only, and Q of each. So FIQ. So these are not excellent Morse functions. The critical values can be multiple, but there has to be an intermediate level. And all the index I plus 1 critical points are up here. They may have common values, common critical values, and all the I minus 1 critical, all the I critical points are here. And that's what, and there are Q of them. That's what FIQ is. Last time, well, this is a stratified space. It inherits a stratification from the stratification of all the functions, but we know what the strata are. The codimension 0 strata are the excellent Morse functions where there's no coincidence of critical values. Codimension 1 are where there's one pair of critical values, one pair of critical points that has the same value. Codimension 2 would be either two different pairs with the same critical value or three with the same value, and so on. And in general, what stratum you're in is determined by the multiplicities of the various critical levels in order. That's the stratification. So in fact, we saw the local structure of this thing. Well, the stratification gives a triangulation. And that's called the nerve of the stratification. The vertices of this triangulation are simply components of a stratum. It can be a stratum of any codimension. So you take all the strata of various codimensions and you take the components of all of those, and they make the vertices of this simplicial complex. And then a simplex is simply a collection of components. A Q simplex would look like this, where this inequality AI plus 1 means that the closure of AI contains AI plus 1. So for example, if you had a codimension 1 stratum bordering two codimension 0 strata, you would have three vertices, two vertices coming from the codimension 0 strata, one from the codimension 1 stratum, and then you would have, because the codimension 1 stratum is in the closure of each of the codimension 0 stratums, you would get this sort of simplicial complex. And we saw that, okay, so we understand the nature of the complex around the codimension 1 strata. And in fact, we know what the nature of the complex looks like everywhere. And it's based on the stars of the barycenters of the first barycentric subdivision of a simplex inside the second barycentric subdivision of a simplex. So this is the case. The dimension of the simplex will be the codimension of the stratum. This is the case of a 1 simplex. So I have a 1 simplex. This is its barycenter. And then this configuration is the star of the barycenter in the second barycentric subdivision. To go one more, if we had the codimension 2 stratum corresponding to a triple point, then we get a 2 simplex. Take the first barycentric subdivision. There's the barycenter of the first barycentric subdivision, and the triangulation would then have this sort of picture around the barycenter. You'd have some triangulation like this, okay? In the other case that I've talked about in codimension 2, we could have the intersection of two of these codimension 1 strata, and that would then produce the product of what we had in codimension 1 with itself. That would give a picture like this, and the way it's triangulated is like that. The codimension 2 stratum, which is here, is in the closure of every one of the 4 components and every one of the 4 components of the codimension 1 stratum, so you get a triangulation like that. Now, in fact, it's more convenient to work with a cell complex structure on this thing rather than the simplicial structure. So fewer cells. And in the cell complex structure, the cells of dimension I are in 1-to-1 correspondence with components of the stratum of codimension I. So the zero cells are just the components of the codimension 0 stuff here. These are the excellent Morse functions up to deformation through excellent Morse functions. The codimension 1 cell is this thing. The codimension 2 cell is this star of the codimension, the vertex corresponding to a codimension 2 stratum in the triangulation. So the cells, these are the usual sort of dual complex. If you take a barycentric subdivision of if you take a triangulation, you take in the barycentric subdivision, there's a dual cell complex. That's really what we're doing here. So the cells, so associated to a vertex, say I of codimension I. So this is a component of the stratum of codimension I. You consider, say AI naught, you consider all simplices A naught greater than A1 greater than AI minus 1 greater than A naught I. This fixed codimension I simplex. And that's it's called the star of A naught. It's all the simplices that contain A naught as the bottom vertex. It's a star of A naught, and this is a cell in this simplicial complex. And it's easy to see that the union of the cells is the whole nerve. And this gives a CW structure to this nerve, related dual to its simplicial structure in some sense. So we've already seen the 0 cells are the components of Fi naught, the excellent Morse functions. The 1 cells are in one-to-one correspondence with the components of FIQ, well, FIQ1. So be when two critical values come together, and the local and the cell is just an interval. And in some sense, the codimension 1 stratum is the midpoint of the interval, but it's not part of the structure. The cell is simply that interval. Codimension 2 at a triangle point, that is 3 critical points with the same critical value. Well, I've already drawn that picture, and I'll draw it again. You get a cell like this, dual to the vertex. And the other codimension 2 is when you have 2 codimension 1 crossing. So that's 2 pairs of critical points with the same critical values. Then the dual picture, the cell is simply a square. So this is the cell. So we understand completely what the codimension 1 and codimension 2 cells look like, and the higher ones are products of stars of barycenters in simplices. Yeah, right, in simplices. So if you have, for example, a stratum where this is what the structure of the critical points looks like, say, then you would have a 2 simplex associated with, sorry, a 1 simplex associated with this pair, and a 2 simplex associated with this pair, and you would take the product of the 1 cell that this gives you and this hexagon, the 2 cell that this gives you. So you'd have a product of the 1 cell and the 2 cell, just based on these 3 values, just based on these 2. And in general, if you have more multiple values, you get products of these stars of the barycenter in the first barycentric subdivision, the star in the second barycentric subdivision. So that's what this cell structure looks like. Okay. Now, last time, well, one more definition from last time. We say that an excellent Morse function, or in fact, it's something that's true for the whole component, is homologically trivial if, well, the critical points are ordered. These are the ones I plus 1. These are the ones I. If these 2 kill each other algebraically, and these 2 kill each other modulo this pair, and these 2 modulo that pair. Okay, so these lines mean the pairing between them is 1, so they annihilate each other, at least algebraically. But of course, in high dimensions, we have Smale's theorem, which says if they annihilate homologically, then in fact, they can be made to annihilate geometrically, which means that this function f is the initial point of a diagram whose graphic looks like just deaths that kill these points in pairs one after another, no crossings. Okay. So then the theorem that we have to prove, the theorem that gives us the pseudoisotopy theorem, is that if gamma is a good path in this, what I'll call phi IQ, which is the nerve of FIQ, the nerve of this complex I've been talking about, the nerve of these Morse functions. It's a good path. Sorry, I'm confusing too. If it's a good path in FIQ with endpoints that are homologically trivial. So that's gamma naught, F naught equals, and F1 equals gamma 1. They're both required to be homologically trivial, and we have a good path. That implies F naught and F1 are in the same component of the excellent Morse functions. Another way to say that, equivalently, if we have a combinatorial path in this cell complex I've been talking about, with vertices homologically trivial. So the vertices of this complex are the components of the excellent Morse functions, going with the code-dimension 0 strata, the assumption is that both endpoints of this combinatorial path lie in these homologically trivial components, then that implies, in fact, that gamma is a loop. That is to say, its endpoints lie in the same component and therefore represent the same point in this cell complex. Okay, so it's a statement about, in this form, it's a statement about this complex and paths connecting homologically trivial vertices of 0 cells in this complex. And last time I showed you how this implies the pseudo-isotopy theorem. Okay, so I just recall, I'm not going to give the argument again. This implies pseudo-isotopy. So that's what we're interested in proving. We're interested in understanding this complex. We understand it locally. I've given you a complete description of this thing locally. In terms of these products of barycenters, products of the stars of barycenters in these simplices, but we have to understand its global structure. All right. And the way I'm going to do that is I've got to split this complex into two pieces. A piece that carries the information about the critical points of index I plus 1, and a piece that carries the information about the critical points of index I. So I need some uniform way to separate the points of index I from the points of index I plus 1. And we do that through intermediate submanifolds. So an intermediate submanifold is a submanifold in W cross I such that the critical points of index, well, intermediate for a function f, the critical points of index I plus 1 of f lie in what I'm going to call Wm plus. That's the part, if this is M, the part of the cylinder that lies above M, and I have similarly Wm minus the critical points of index I for F lie in Wm minus, in the interior of these things, and no critical points on M. So M is a regular level that separates critical points of index I plus 1, they're above M, critical points of index I are below M. Okay. Now, in fact, it's easy to see that, consider the subset of these functions where f inverse of 1/2 is intermediate. So this condition simply means the critical values of critical points of index I plus 1 are greater than 1/2, and the critical values of index I minus 1 are less than 1/2. I should say this is a level. I guess I never really said that. So this is f inverse of some t. It's got to be a level for f. It's not surprising that there's no essential difference between these and these. Fiq is isomorphic to Fiq tilde cross an open 2-disk. Well, maybe not a 2-disk. Anyway, it carries all the stratified information, the homotopy information, so we can restrict attention to Fiq. In fact, the stratification of F tilde IQ is equal, well, the nerve, that's what I should say, the nerve of FIQ is equal to the nerve of FI. FIQ tilde is equal to the nerve of FIQ. There's no difference as far as the stratification is concerned between considering all functions and considering those for which 1/2 is an intermediate. That's simple enough. I won't say anything about it. Okay, let's let M be all intermediate levels for all F in F tilde 1Q tilde IQ. And then we have a map from F tilde IQ into M that sends F to F inverse of 1/2. And this is a smooth map, of course. And it's not hard to see that it's a locally trivial vibration. It's also, the map is on too. Not hard to see either. Okay. So let's let F sub M be the fiber over M. So M is an intermediate manifold. And we can form its strata, it has an induced stratification. We can form the nerve associated with its stratification in the cell complex. We also have this F, the nerve associated to F tilde, which is the same as the nerve associated with the original Morse functions. And there's the inclusion of the fiber into the total space is a stratified map. So there's a cell map here. You might think that this is an isomorphism. For example, if M is simply connected, if the base is simply connected and you have a locally trivial smooth stratified fibration, which is what we have here, then you see that every stratum in M, if M is connected, pushes back to include a stratum from any fiber. And if the base is simply connected, that will give you an isomorphism. In general, the fundamental group of M based at wherever fiber we are acts. So pi1 of the space modulo M acts on this stratification. So acts on phi M by cell maps. And it's the quotient phi M modulo pi1 of M that is the stratification of FIQ tilde, which is phi IQ. So the stratification of M can be, and in fact is in general, bigger than the stratification of all the Morse functions, because this is possibly non-trivial action of the fundamental group of M based at script M based at little m on this cell complex, and it's the quotient that's equal to the stratification of the whole space. I mean, just as a simple example, suppose you think of the Mobius band. So let's think of, here's a stratified space with two strata of codimension 0 and one stratum of codimension 1. We do the Mobius band. And you see that this is a locally trivial stratified fibration, but when you come back, you only you have this action on the fiber. So the stratification of the Möbius band is well, that didn't work very well. The stratification of the Möbius band is one stratum of codimension 0 and one stratum of codimension 1. So you started with a picture like this. You had an involution, the action of the fundamental group. So the quotient picture looks like that. Okay, so that's what happens in general. Okay. Now, I mean, the other, sorry. I should say, I have to be a little careful about components. So suppose I have a manifold M in this set of all intermediate manifolds. It's contained in some component. So this is a component or path component. And all the information I can get using the fundamental group will be about the inverse image of this path component inside F tilde IQ. So what I really have, I should have said, is F tilde IQ 0 fibering over M naught, which contains M, and then the stratification of this thing will be the stratification of the fiber divided by the fundamental group of this component. Okay, but there's a little lemma that says with n greater than or equal to 6, pi 1 of v equals 0, this sort of standard pseudoisotopy hypotheses implies M is connected. So I don't have to worry about passing to a component. This is just an argument by induction on the number of critical points, using the fact by Smale's argument that you can always annihilate a pair of critical points, and then the birth-death theorem that says, so you annihilate, then you know the two intermediate manifolds are isotopic, you line them up, then you do the birth, that takes you back to the original situation, and you can cancel the birth and death. So I won't go through that argument. So in fact, we don't have to worry about these components, and this space, this cell complex we're interested in studying is phi of M modulo pi 1 of M naught M. The next thing I need is some information about this fundamental group. Sorry, not M naught M, just connected. So let's let G sub M be the subgroup inside the component of the identity of the diffeomorphisms. So those diffeomorphisms isotopic to the identity such that stabilize M. So fix one of these intermediate manifolds M and look at the diffeomorphisms, not the identity on M, but that bring M back to itself. And the claim is that pi naught of this group of diffeomorphisms maps on to pi 1 of M. Okay. So what is this? Sorry, I've got the map the wrong way. Sorry, that's not what I want. There's a map, I claim there's a map from pi 1 of M into pi naught of G M, the stabilizer of M in the component of the identity of the diffeomorphisms. And how does that go? So an element in pi 1 of M is an isotopy of M mu mu t of m, starting at the identity, well, starting at the inclusion, and with mu 1 of m equals mu naught of m. So it's an isotopy starting at the identity and ending with the same embedding, with the same image as where it started, but not necessarily the same map. Well, you can extend isotopies to ambient isotopies. So there's some psi t mapping W into W starting at the identity, and psi t restricted to m is mu t. Okay. So psi 1 is an element in the diffeomorphism group stabilizing m and the component of the identity. Psi 1 is connected to psi naught by a family of diffeomorphisms, so it's in the component of the identity, and the condition that mu 1 of m is the same image as mu naught of m says that this diffeomorphism actually stabilizes m. So any element in the fundamental group leads to an element in the group that stabilizes m up to isotopy. You deform this by homotopy, you'll deform that by isotopy. And it's onto, since pi naught of the diffeomorphism group is trivial. So if you have pi naught of the component of the identity of the diffeomorphism group, if you have any diffeomorphism here, it's isotopic to the identity, so you can take that isotopy and run this argument backwards. So this tells me that phi of m modulo pi 1 of m is the same thing as phi of m modulo pi naught of the diffeomorphisms that stabilize. Diffeomorphisms isotopic to the identity that stabilize m. And we're going to call that group capital pi. Okay. All right, now we're ready to do our splitting into two pieces. Because this complex of stratified space of functions that have m as the one m is an intermediate value and equal to f inverse of 1/2, you can simply split into the stratified space of the way the critical points of index I plus 1 act, and the stratified space of the way the critical points of index I act. So this is comes from the stratification of diffeomorphisms of Wm plus, and this comes from the diffeomorphisms of Wm, well, I shouldn't say diffeomorphisms, I should say these functions f I plus 1 critical points of index I plus 1 and q of them, and here critical points of index I and q of them on W minus m. So the same sort of structure we've been talking about. Here you would be studying only the critical points of index I plus 1 and their coincidences. Here you would be studying the critical points of index I and their coincidences. Well, that structure is exactly the product of the two components. I mean, you have to worry about matching the maps along m, but that's a contractible space. So. Okay. So this is the complex we need to understand pi m mod, what I'm calling capital pi, and I've broken phi m into the upper and lower pieces. And that's what we're going to study through the group GLQZ. So now we get to the K theory. We're going to build a complex associated with GLQZ and show it's related to this product. In other words, to phi m, and we're going to understand the action of pi, what it's related to in terms of an action of this group GLQZ, which I'm going to call GQ, on the complex. So we're going to build a complex using the lower triangular subgroup inside GQ. So matrices that have, since we're working over the integers and these are invertible matrices, the diagonal entries have to be plus minus 1, and then you have arbitrary integer entries below the diagonal. So that's TQ. And the other thing we need is the symmetric group, which is naturally embedded in GQ. The permutation SI that switches I and I plus 1 is represented by the matrix. So this is I and I plus 1, I and I plus 1, and other than that, it's just the identity matrix. Okay, zeros out here. So this is the standard representation of the symmetric group inside the general linear group, SI being the element that interchanges the ith and I plus first basis vector that's given by this matrix. Okay. Now, you might wonder what these have to do with these critical points and orderings of the critical points. And let me just point out the basic fact to you. So these are the I plus 1 critical points. I want to associate to this collection of critical points a basis for HI plus 1 of WM plus comma M. This is M here, and all of this is WM plus. Okay. Well, how do I do that? I take descending manifolds for these from these critical points. Right? These descending manifolds give me relative homology classes, and they, of course, make a basis, no matter how I do it. But the descending manifolds are not unique. The first one, unique, we would say up to homotopy or their homology class, whatever. The first one is unique. So the bottom one is unique. What about the next one up? Well, remember the handle slide moves. These are critical points, all of the same index. So they're these elementary handle slide moves. You can change the homology class of the descending manifold from critical point Q minus 1. This is critical point Q minus 1, and so on. Here's the top one, critical point 1, by adding any multiple of the class of critical point Q. So as you take this descending disk, you will pass the lower critical levels. In this case is exactly one lower critical level. And when you pass that critical level, you have a choice to make. You can deform this by a path, by a path of embeddings that has an intersection number 1 with the ascending manifold. And that would change the homology class by 1 times this descending disk. And that's the basic move we've used in proving the H-cobordism theorem. But I can only do that with critical points below the one that I'm descending from. So the bottom one, there's no choice. There's no other critical points below it. So it's a well-defined homology class. The next critical point gives me a homology class well-defined modulo the lower ones. So what am I getting? I'm getting a basis up to the action of the lower triangular group. Okay, so getting a basis is an isomorphism from the free abelian group, say generated by the cells, into HI plus 1. And I could first act by any lower triangular isomorphism and change the basis. So this basis would go to that one. And of course, I forgot to say, the other thing I have to do is I have to orient the cells so I can change the orientations. That's why I have to allow plus minus ones on the diagonal. And that corresponds to changing the orientations of the descending manifolds. So you can think of a choice of ordering of the critical points, C1 up to CQ, is really the same thing as a basis, an ordered basis of HI plus 1 up to TQ action. So if you will, the set of bases we're thinking about is GQ mod TQ. So when you see these critical points, you don't have the descending disks. This is the ambiguity in choosing the descending disks. So you don't get a basis, you get a family of bases up to the action of TQ. All bases, of course, G changes any one basis to any other. So different, well, that's all I want to say about that. So that's why the lower triangular group is coming in. And what about this symmetric group? What's happening there? Well, the symmetric group is related. You see pieces of the symmetric group coming in when two critical points coalesce. So if two critical points have the same critical value, then you have two ways to turn this into a fully ordered, two ways to get into an excellent Morse function. You have to move one of them up and the other one down, or anyway, relative to each other. And the symmetric group acts on that. So the symmetric group is coming in when you have these coincidences. If I had 3 coincidences, then I'd have the symmetric group on 3 letters coming in. And we get the same sort of combinatorics that we were talking about earlier with the cells associated with these lower strata. So that's these two, and we've seen these two ingredients. We didn't label them this way. They were essential ingredients that came out of the construction of the stratification of the Morse functions. And now we're seeing them in terms of handles and orderings of the critical points. Okay, so we're going to make a complex whose 0 cells are the set of bases up to this action of the lower triangular group. So set of bases up to, well, let me say what this is in a different way. This is the space of complete flags. These are integral flags in a lattice of rank Q. So by that, I mean you have the lattice of rank Q, and then you have maybe L1 included in L2, included in LQ minus 1. This has rank 1. This one has rank 2. This one has rank Q minus 1, Q minus 2, and so on. So each Li is a direct summand. And Li has rank Q minus I. So for example, at the bottom, we start off, we have a line, copy of Z primitively embedded. L2 is a plane, but it's a free abelian group of rank 2, which is a direct summand, and then so on. So it's a complete flag. We're not working continuously over the reals or the complexes. We're working with integral lattices. So I do need to say that each one of these is a direct summand. Okay. Well, you have the standard flag. You have you have the standard flag, which is the span of the last basis vector, the span of the last two, and so on, up to the span of all of them. This is a standard flag inside ZQ. And TQ is its stabilizer. You let TQ act. It acts non-trivially on ZQ, obviously, but it preserves this flag. It sends EQ to plus or minus EQ, so it preserves this line. It sends these two back to the same space, and so on. And so the space of all flags, complete flags, is identified with GQ mod TQ. You take the standard flag and you act by GQ and you get a new flag. But if you changed by right multiplication by TQ, you wouldn't change the flag. So this is the space of maximal flags inside standard vector space. So that's going to be the vertices or the zero cells of the complex that I'm going to call psi Q. Okay. The one cells, well, one cells, of course, are going to be intervals. So the question is, if this is a flag, there's going to be a one cell for each generator, standard generator of the symmetric group. I have to say, if you have a flag, how does this interval move it to another flag? Okay. Well, if the original flag comes from G times the standard flag, then SIF comes from GSI times the standard flag. Okay, so in the standard flag, let's look at LQ minus I guess, over LQ minus I plus 1. Let me not worry about the indices, how they're related to I. So somewhere in the flag, I have an LR and an LR minus 1, LR minus 2, and so on. And the SI is interchanging these two. Well, so this was, I guess, EI up, EI plus 1 up to EQ, and this is EI up to EQ. Okay, so SI interchanges EI plus 1 and EI, so it would send this part of the flag to this. Here's EI plus 1, and here's EI. Okay. So that's what SI does. It doesn't do anything below here and doesn't do anything above here. It only changes, actually, it only changes this element in the flag. So this plane, this corresponds to the 2 plane in this picture. It's the same 2 plane. What's changed is this line. So the line went from being the span of EI plus 1 to the span of EI, of course, plus the lower stuff. So that's an elementary change. So when you look at the flag, you're coming up, you have FR minus 1 included in FR. This gets, FR is unchanged. The lower stuff is unchanged. And FR is sent in FR prime. If I work in FR mod F minus 2, you simply see a change from here to here. So you have this 2 plane, FR mod FR minus 2, and you have 2 different codimension 1 copies of Z. But as you can see in the standard model, these 2 together form a basis. So their intersection number, if you will, is 1. That is to say, this copy of Z1 and this copy of Z1 prime, form a basis or form a direct summand of this plane, FR mod FR minus 2. So you're not allowed to replace this integer vector by an arbitrary primitive embedding of Z into this plane. It has to be one that has intersection number 1 in this sense. Together, a basis for this and this make a basis for the plane. And there's a similar sort of thing if we were to look at, say, SI and SJ, the group spanned by those 2 where they're separate, so I and J are greater or equal to 2, then in this flag, you would find 2 different planes at different places in the flag, and you would do these sort of transformations in this one and in that one. So you would produce 4 different flags by doing these switches here and here. And the other possibility is when you have SI and SI plus 1, then you see a 3-dimensional space, and you have various changes inside there, but they satisfy SI plus 1, SI, this usual relation in the symmetric group, okay, which is that triangle relation that we've seen before. Okay, so we're going to make a complex with 0 cells, GQ mod TQ. 1 cells have a type SI for 1 less than or equal I less than or equal to Q minus 1, I guess. These are the elementary interchanges, and you can go from a flag to SI of the flag. This is given by G times the standard flag. This is given G times SI of the standard flag. But it depends, you have an integer associated to each edge. The two-dimensional cells where exactly the ones I've talked about before. You have a flag, SI of the flag, SJ of the flag. Here I and J differ by at least 2. And over here you would have SI, SJ of the flag, which is also SJ, SI of the flag. And then you'd have this 2-cell with these 4 vertices, 4 0 cells, and these 4 1 cells. In case it's SI and SI plus 1, you get a picture like this: the flag, SI of the flag, SI, SI plus, I guess, SI plus 1, SI of the flag, SI, SI plus 1, SI of the flag, and you can go the other way: SI plus 1 of the flag, SI plus 1 of the flag, and then across here, and use this equivalence relation. And you would put a 2-cell in with these 6 boundaries, the hexagonal boundary. Okay. In general, you think about the symmetric group acting in the natural way on delta Q minus 1, and you look at the star of the barycenter in the first barycentric subdivision, the star in the second barycentric subdivision. So let me just draw the picture again for the 2 simplex. The star looks something like this. So the symmetric group is acting by permuting the coordinates here. And you see that the symmetric group actually acts freely. The vertices are a single orbit of the symmetric group. And if I pick one of them, the sort of basic simplex where these go in order, maybe x0, x1, x2, then you identify the vertices with the elements in the symmetric group. You'll have a cell in this complex which connects these 6 as a 2-cell with these 6 0 cells and these 6 1 cells as its boundary. So the cells associated to subgroups of the symmetric group, given by these coincidences that we've talked about before. The first 2 are equal, then the second one's different, and the next 4 are equal, and the next 2 are equal, then the last one's different. This would give me an interval, 1 simplex, cross a 3 simplex, cross a 1 simplex, and I would take the product of the barycentric subdivisions. The vertices of that product would be identified with the product of sigma 2, sigma 4, and sigma 2, and that cell would be embedded as a cell in this complex. So that's the complex, psi Q. And now we can go from psi m plus to psi q by simply fixing a basis for hi plus 1 of wm plus comma m, that is to say an isomorphism zq to hi plus 1. Then let's think about what happens on 0 cells. 0 cells are orderings of the critical points. The orderings of the critical point then give you a basis in the homology up to the lower triangular group. But if I've identified the homology with the standard lattice, that would give me a basis in the standard lattice well defined up to the lower triangular group. That's exactly a vertex in this complex associated with the general linear group. And the fact that these pictures that I've been drawing are the same says that so that's a map from 0 cells. 0 cells on both sides are cells of an arbitrary dimension on each side are determined by the vertices. And you see fairly straightforward, in a fairly straightforward manner, that every cell in the domain maps then to a cell in the range. And in fact, this map is a local isomorphism, i.e., it's a covering map. Okay. So the local structure of this complex and the local structure of this complex are exactly the same, and they match under this map. So locally, this map is an isomorphism. You don't yet know globally that it is an isomorphism, though that's what we're going to eventually see. So what this is starting to compare is the upper half of this combinatorics associated with the way the critical points are ordered with just this algebraic thing in the general linear group. And likewise, there's a map from phi m minus to psi m. This will be a covering, and it requires a basis for hi of wm minus mod m. All right. Okay. I'm going to call these maps W plus and W minus, but or omega plus and omega minus. So omega plus, omega minus depend on the choice of basis. But of course, if you vary either one, you simply vary by an automorphism of this complex given by multiplication by an element in GQ. Okay. Different choices vary by action of GQ, clearly. All right. All right. Okay, now we can't choose our bases. Well, we're much better off if we don't choose our bases independently, but choose them so that they preserve the pairing. So remember, hi plus 1 of wm plus m and hi of wm minus m are dual. And one way to think of it is it's Poincare duality. Another way is just to take the boundary map from hi plus 1 of wm plus m into hi of m, and the other one hi of w plus m into, sorry, hi minus 1 of m. And these are dually, the intersection here I'm sorry, I've done something wrong here. Yeah, it would be hi of wm minus mod v, so it's h n minus I. Right, those are the ascending manifolds, they're n minus I manifolds. So here I would have h n minus I and h, let me get some more room here. H n minus I of w minus m into h n minus I minus 1 of m. Right. Well, I mean, this is slightly tricky if these two numbers are equal, but if they're not equal, then these are just the full groups. These would be isomorphisms if they're not equal. And those groups are dual, and that's the Poincare duality pairing, or the intersection pairing between the descending manifolds and the ascending manifolds. These two numbers can be equal. When they are, these maps are not isomorphisms, but they're embeddings into half-rank dual subgroups of this middle dimensional group. And once again, they're dually paired. So that's the pairing we're talking about. And now we want to consider bases phi from zq to hi plus 1 of wm plus mod m, and phi naught prime from zq into n minus I of wm minus z, that carry the pairing here to the standard duality here. In other words, under the pairing between these two groups, which I'll write as a bracket, phi naught of ei and phi naught prime of ej pair to give delta ij. So the duality pairing here, these bases are set up so that the duality pairing here becomes the standard duality pairing from the basis in ZQ. And now we want to see if phi naught prime is a dual pair. We'll call these dual pairs. Then so is phi naught acted on by G, and phi naught prime acted on by G transpose inverse. Okay, so let me just check that for you. So we want to take phi naught G of EI paired with phi naught prime G transpose inverse of EJ. Well, this pairing is simply given by taking the transpose, the dot product of the transpose of this element with this one. So that's G transpose phi naught of EI dotted with phi naught help. This is obvious. Let's see. I take EI act by G of it. Oh, I see. So this is EI transpose dot EJ. So in general, the statement that phi is phi and phi prime are a dual basis pair is that phi of x, phi naught of x, phi naught prime of y for general x and y is simply x transpose y. That's what you get from this by linearity. Okay, so now I want to apply that here. Phi naught g of EI, inner product phi naught prime transpose g inverse of EJ. Well, here I have phi naught and phi naught prime, so I'm supposed to take the transpose of GEI dotted with transpose G inverse EJ. Well, this is EI transpose, G transpose, G transpose inverse EJ, which is just delta IJ. So this is the condition. So the condition that when you act by a pair of elements, so said another way, phi naught prime is a dual pair, then phi naught G, phi naught prime H is a dual pair if and only if H is G transpose inverse. Okay. How am I doing? Oh, I'm out of time. All right, well, I'll just say what the punchline is. The map pi onto GQ, the natural map is onto, and you get a commutative diagram here. This is an isomorphism of complexes, and this map is onto, and that implies that phi m modulo pi is psi q cross psi q modulo this diagonal action we've just been talking about, PQ. Those are actually isomorphic. And then the homologically trivial vertices in phi m map to the orbit under GQ of the identity, comma the identity. So if you have a path in here, combinatorial path in here, whose endpoints are homologically trivial, then both endpoints lie in the orbit of the base point here under the GQ action. And therefore, when you project the loop down here, you get when you project the path down here, you get a loop. But this is an isomorphism, that means it's a loop here. And therefore, the starting and end points, the functions, any representative functions are in the same component of F naught. and hence connected by a path with no critical points, which is what we needed to prove. Now, in order to show the fact that this homomorphism groups is onto isn't very hard, to show that this map is an isomorphism, this one, I know that I know that this is a covering projection, and you have to then study the elementary paths in this space that start and end in GQ, and show that any lifting of them back to this space, it starts and ends in pi. And there's a simple set of generators of length 1 or 2, or paths of length 1 or 2 in the CW structure that generate all the paths, and you just check one after another that they all lift to paths in here with endpoints in the same orbit of pi. So that's how you prove this map is actually an isomorphism. Then you take quotients and you get what you want. Well, that's a very brief summary. That's all I had time for. I didn't quite have time for that. Those of you who stuck in all the way through, I hope you got something out of it, got some sense of how this argument goes. In the end, it's very intricate and somewhat complicated, but there are only 2 or 3 ideas. One of them is this idea that Serif uses over and over again. You want to study a general path, you break it up into individual components, which are much simpler, and you study those one at a time. And finding exactly the right way, which subspaces you should use to break up the paths, is sort of the basic modus operandi of his argument. And then in the end, this homological stuff it's not so difficult. I didn't have time to present it, but it uses the same sort of ideas that we've already seen over and over again. Anyway, for those of you who stuck in all the way, thank you very much. I enjoyed going through this material. I hope you got something out of it too.
Thank you.
I forgot the champagne, so we'll have to do it privately later. All right.
Thank you.
Yeah.
Thanks for teaching.
Stay safe. Have a good Christmas.